Hi everyone, the project proposal is addressing food insecurity in Wisconsin. Food insecurity is a significant issue affecting millions across the United States. Research shows that in 2023, 47.4 million people experienced food insecurity. Wisconsin highlights some of the most glaring disparities in food insecurity rates nationwide. Between 2015 and 2019, 7.4% of white households in Wisconsin faced food insecurity. However, for racial and ethnic minorities, these rates were 3 times higher. The effects of food insecurity go far beyond hunger. They impact physical health and mental well-being, leading to higher levels of stress and anxiety. Economically, food insecurity affects productivity, trapping individuals and communities in circles of poverty and health inequities. Our proposal aims to address these disparities by analyzing key data to identify accessible and affordable food options for specific demographic groups. By leveraging this data, we hope to inform strategies for Feeding America Eastern Wisconsin team, ultimately improving food access and promoting healthier eating habits among the state's most vulnerable populations. This project utilized data from several key sources. Feeding America Eastern Wisconsin provides detailed records of food distributions, including the types of food offered, quantities, and weights across various counties. Additionally, social vulnerability matrix and demographic data such as poverty rates and uninsured rates, etc., providing context on which populations are most in need. These data sets are substantial and updated by month, offering a dynamic view of the situation across Wisconsin. For example, by analyzing trends over time, we can identify areas where food insecurity is worse and anticipate future needs. Many datasets had missing data, such as gaps in social vulnerability metrics, which we addressed using imputation techniques, predicting missing values based on existing data patterns. Furthermore, datasets were normalized to ensure consistency, unifying formats and eliminating inconsistencies such as spell errors or mismatched cases in county names. Our proposed solution takes a unique approach, utilizing a hybrid NoSQL architecture that combines the strengths of 4 specialized database types. There are white column database, document database, graph database, and key value database. Then we're tying it all together with Apache Spark, which serves as the central processing engine. This is hybrid system ensure flexibility, scalability, and efficiency. Cassandra is the white column database we utilized. It is specifically chosen for handling structured, high ingestion data, such as food assistance records distributed across Wisconsin counties. Cassandra's architecture is ideal for storing large-scale tabular data with flexible schemas. Data is organized into rows and columns, with each row schema customizable. This flexibility is important for managing diverse records while maintaining high read and write efficiency. For example, we use the county as the partition key to group all records related to the county together. Clustering columns such as the month and the food assistance type allows us efficiently retrieve records based on time or category. From this query, select all from food assistance, where county equals Brown and month equals 2023 June. It retrieves all food types data for Brown County in June 2023 efficiently. Leveraging Cassandra's design to optimize access, Cassandra's ability to handle large data sets makes it an important part of our architecture, ensuring reliable and fast data processing. Next is MongoDB, our document database, which handles semi-structured data. This is especially valuable for storing social vulnerability metrics, where attributes like poverty rates or uninsured rates can vary between counties and over time. MongoDB uses a schema-free JSON-like document structure, allowing us to store dynamic, nested attributes. For instance, a record for Brown County in June 2023 might include fields like the month and county, as well as a nested object for social metrics such as poverty and minority population rates. This flexibility enables us to easily add or modify fields as the dataset evolves, avoiding the rigidity of traditional database. Additionally, MongoDB supports powerful aggregation pipelines, making it easier to analyze trends and average across counties. For example, using MongoDB aggregation, we can calculate the average poverty rate across all counties. This capability allows us to generate insights that inform equitable food distribution strategies. Neo4j is the graph database in our system, chosen for its ability to model and analyze complex relationships between entities like counties, food types, and social metrics. In Neo4j, data is represented as nodes and edges. For example, a county is a node with properties like population or poverty rates. Food assistance types are also nodes connected to counties through offers relationship. These relationships define the types of assistance each county provides. This structure allows us to explore interconnected data efficiently. For example, we can query Neo4j to find all food types offered by Brown County and retrieve associated weight and quantities. The graph-based design provides insights into correlations, such as how poverty rates influence the demand for specific food types, enabling us to identify patterns and optimize distribution strategies. Redis, our key value database, is a high-performance caching layer designed for real-time analytics. Its simplicity allows for rapid storage and retrieval of frequently accessed data. In Redis, each record is stored as a key value pair. For instance, the key Brown 2023 June 1st non-foods might map to a JSON object containing details like weight, quantity, and poverty rate for the non-food type in Brown County during June 2023. This structure ensures that each record is uniquely identifiable, enabling quick lookups. Commands like get allows us to retrieve this data instantly. Supporting applications that require real-time insights, Redis is particularly useful for operational dashboards, where stakeholders can access up-to-date data without delays, making it a required component for fast and efficient reporting. Finally, Apache Spark serves as the central processing engine for our architecture. Its distributed computing framework allows us to integrate and analyze data across all 4 database types seamlessly. Spark connects to Cassandra for structured data, MongoDB for semi-structured metrics, Neo4j for relationships, and Redis for real-time records. It processes these diverse datasets efficiently, performing complex transformations and joins. For instance, Spark can join food assistance records from Cassandra with social metrics from MongoDB to generate insights about high-need areas. This unified approach ensures that no data source was separated, enabling comprehensive and actionable analysis. Spark's scalability and fault tolerance makes it indispensable for handling the large and dynamic datasets required to solve food insecurity, empowering stakeholders to make informed, data-driven decisions. Our hybrid architecture is designed to overcome the challenges of working with large, diverse datasets. The three key reasons why this approach is so effective are: first, is scalable. The wide column database Cassandra can handle massive volumes of data without performance degradation. This is significant as the scope of food distribution expands, or as we incorporate additional data sources in the future. Second is flexible. MongoDB allows us to adapt evolving data needs, accommodating changes in the types of metrics we collect. This flexibility ensures that our system remains relevant and useful over time. Third, it provides deep insights. Neo4j's graph modeling capabilities allows us to uncover relationships and patterns that might go unnoticed. For example, we can analyze how poverty rates in specific counties correlate with the types of food assistance most in demand. Using this system, we can identify counties where high poverty rates appeared with low food assistance availability at the same time. We can then predict future demand and allocate resources proactively. This predictive capability not only optimizes resource distribution, but also ensures that no community is left behind. While the hybrid architecture offers powerful capabilities, it still contains limitations. First, we rely heavily on external datasets, which may contain missing, outdated, or inconsistent data. Despite employing imputation and validation techniques, these methods cannot fully eliminate risks to data quality, potentially reducing the accuracy of insights. Second, the integration of 4 distinct database types introduced a significant complexity. Each database is optimized for specific use cases, but balancing their trade-offs, especially as dictated by the CAP theorem, can be difficult. For example, wide column and a key value database prioritize availability and partition tolerance, which might lead to eventual consistency issue and affect the accuracy of real-time analytics. For alternative approaches, one option is to use a fully relational database to handle all data types uniformly. While this would simplify integration, it would compromise scalability, particularly for semi-structured or relation-based data. Another option is a phased rollout. We could begin with just wide column and document database to establish a core analytics pipeline. Once the system is stable, we could incorporate the graph and key value databases in later phases. This approach reduces risk by allowing us to test and optimize each component before fully integration. Lastly, we could explore cloud-based database solutions. These platforms provide scalability, high availability, and fault tolerance. However, cloud solutions come with increased operational costs and dependency on third-party providers, which might not align with our project's budget constraints. Finally, this visualization is the architecture of our hybrid system. As you can see, data from multiple sources flows into 4 specialized databases. Apache Spark integrates these databases, enabling unified analysis and seamless data processing. Cassandra manages high ingestion structured data efficiently. MongoDB handles semi-structured data, offers flexibility. Neo4j uncovers relational insights, and Redis ensures rapid access to important information. Altogether, they form a powerful system. This system has the potential to not only transform food insecurity in Wisconsin, but also serve as a model for this challenge nationwide.